Next thing we're going to do is inverse functions. Okay, so we're getting familiar with function notation, and they've given us two different functions. And actually, this is two different questions. I didn't really label it that way, but I probably should. We'll call this A, and we'll call this B. In A, they're asking us, they have this brand new notation, f, and it looks like it's to the power of -1 with the variable x in the function. This is called an inverse function. Graphically, which maybe they didn't talk about, graphically what this is taking a function. So for instance, a quadratic, which you're probably pretty used to or annoyed with, depending on how you feel about it. Taking a quadratic or the graphical representation of something, and you flip it on a 45-degree angle. So that the inverse function, I'll draw it in blue, would actually, it would look like, oh, that's a straight line, would look like this.
Why?
Well, that is what an inverse will do. So I'm going to show you the algebra to it, and if we were to graph it, that's what ends up happening graphically. It's like taking a line right through a diagonal, and you flip everything on that diagonal.
Why did they want to know that, like, when they made this?
An inverse function shows relationships between different types of operations. So the inverse operation of something, for instance, like squaring and the square root of something, they're considered inverses of each other. So this is the relationship, the graphical relationship between those two different operations. And this is the algebra we use to describe the idea. So what I'm going to do is we're going to go through the algebraic process of figuring out what it is.
Okay.
So we have the very first one, f at x. So we have f at x is equal to x over x plus 3. Now, when finding an inverse, it's very common and nothing wrong with it at all for a student to kind of use a let statement and turn our f at x into maybe the letter y. It becomes simpler to handle in terms of notation, just because there's so many symbols in function notation. We're looking at it, f, open bracket, x, closing bracket. Like there's 4 symbols. And if we go through the algebra moving this thing around, which in itself is a variable, it can get a little convoluted. So I'll do it with a let statement just to show you why and how that might make it simpler. So what a let statement does is it simplifies a question. I'm going to say let f at x, technically that's a variable, equal y. And instead of moving 4 symbols, I only have the letter y to move around. Algebraically, that's going to be a little easier for us to look at. So we're going to say y is equal to x over x plus 3, okay? Now my next step is to actually carry out the inverse, okay? So I'm actually going to carry out the inverse here. And what happens there is you take your y values and you substitute them in for the x values. And you take whatever x value you have and you substitute it in for the y value. So what that would look like is x is now where the y was. And we now have y's where the x was. So we've changed their places algebraically, okay? Now what we need to do is we need to isolate. Isolate, there we go, L-E-T. That's not correct. Why can't I spell this word?
What does that mean?
Isolate.
L-A-T-E.
Is it E or A?
It's
Oh, thank you. Okay, I'm not sure why that was so hard for me.
Like isolate.
Isolate, I think. Okay, we're going to isolate for, I wanted to write it down here so we had a step, for y. So the idea here is we need to get y by itself on one side of the equation. So we're going to take this. It's a denominator of essentially a fraction. We're going to move it to the other side. And in order to do that, you have to multiply both sides by that denominator. So y plus 3 multiplied by x is equal to, we still have the y on this side. I'm going to keep the denominator just so that we see y plus 3 again. What we're doing is multiplying both sides by y plus 3.
Wait, I have a question.
Yeah.
What are we like solving for?
We're trying to isolate just for the letter y. And the reason we're doing that is we're trying to get a single variable. Just like maybe if you think back to like linear equations, we're trying to get y by itself so that we can graph it.
I don't remember.
The idea is if we get y by itself, it becomes simpler to graph.
Right.
So currently I have multiple y's in this equation. That gets difficult to graph something. Y's are supposed to be like our outputs, and the x values are supposed to be like what our inputs are. They call them independent and dependent variables. We're going to go through the process, and then essentially what it is we are finding what the inverse is. So this is the process to finding an inverse. So we swapped out the x's and the y's. They're in different positions now, right? So our y was here and these used to be x's. Now an x is here and we have two y's. We're gonna isolate instead of isolata for y. So part of that process is this denominator, I need to get rid of it.
Right.
So I multiply both sides by the same amount. The reason I do that is because on this here, these essentially cancel out. They create a 1, which is very convenient. So now we're left with y plus 3x is equal to y. I still need to isolate for a single y. It does look like I have a y by itself over here, but I still have a y here. I need to somehow put them to be a single y. So this is a bit of an algebraic trick. What we're going to do is we're going to distribute our x's. So this becomes xy.
Plus 3x.
Yes, plus 3x is equal to y. Okay, this is a little better. Oops, I threw in an extra y there. There we go. This is a little better. At least it's 3 separate terms now. I'm going to put all the y's by themselves on one side. So in other words, I'm going to move this xy. I'm going to move it to the other side. When I do that, it just changes its operation. It becomes negative xy. The reason I've done that now is I have a y in both of these. I can common factor out y. And when I common factor y, that's essentially the idea of getting a single y representative. So the idea is I'm dividing both of these by the value of y. When we do that, y divided by y is 1, and xy divided by y is just negative x. Okay, and then on this side we have 3x. So now, this is the important piece, I have a single y. This is what my goal was. I got to isolate for y. So I need to get rid of what's multiplied by our y, which is that, it looks like almost an equation in itself. So we're going to divide both sides by this. And this is a trickier question to find an inverse of, the reciprocal function, just because of the amount of algebra that's involved. On the right-hand side, these disappear. This is it. Y is equal to 3x over 1 minus x. This is technically our answer. The last thing, to make this simpler, even though this was a long process, is I gotta get my let statement back. I technically said let f at x equal to y. I'm gonna do the same thing. I need to substitute my f at x back in. Now, but this is now the inverse. So instead of the original f at x, we have the inverse of this function. So I'm just gonna swap sides because we tend to write it on the left-hand side. The inverse of the original f at x function is equal to 3x over 1 minus x. Now that was pretty long in itself, what we did there. So we're going to do a little bit of a recap. That was quite a bit of algebra. We decided to find the inverse. We put in a let statement so that we didn't have to move f at x around. Otherwise, both of these y's we would have been writing f at x for, which just gets algebraically a bit convoluted. So we made it just one variable, so it's a little simpler to manipulate. And then we went through a process, and you'll have to think about it. It won't be the same every time, of getting y by itself. And then once we've done that, we substituted back in our inverse notation. So the notation for f to the power of negative 1, or the inverse of f at x, is equal to y, and we got our solution to the question. Now, that was a pretty long process, but it's actually really important for the second piece here.
Wait, I have a question.
Yeah.
I don't understand when you divided the y
Hmm.
and like.
And isolated?
Yeah,
that's
I haven't seen that.
Yeah, this is a little algebra trick. So the goal here is, let's use this. I have two y's.
Yeah.
Now, I had known I'm going to do this. So seeing this as a student is really tricky. To be like, how did you think to do this? This is just something, having a lot of exposure to algebra, I realized I need to make this essentially 1. So I knew that I needed to do some distribution. And then when I did that, I'd have separate terms that I can either add or subtract and move on left and right on an equation. And then I got both y's together on one side. I could have moved the third thing here, but that would have made it more convoluted. Like, I wouldn't have been able to common factor. So I knew if I move both of the terms that have a y in them, I can go through a process called common factoring. I took that y out, and then whatever's left, which would be 1 and negative x, I left in the brackets. From there, I need to get this y by itself. So whatever I'm being multiplied, this could have been the number 5. I just have to divide by whatever that is. In this case, it's like a part of an equation, almost looks like. So when it came over here, our denominator looks like part of an equation. And it essentially is. This is our new inverse of a function. This is a tricky piece. That's why we're going to print it for you to take a look at. Okay. What is important is we now have a function for the inverse function, 3x over x minus 1. I'm going to put this back up at top. Okay, it's x minus 1. So we have that negative x, 3x over x minus 1. This is important because in the second piece here, what they've actually asked us to do is plug this into the g at x function and then solve for x, which is another algebraic headache. There's quite a bit to this piece here.
They did?
So I'm going to try to go through it quickly because I know we've been talking for a bit,
Okay.
just so you have an example, but you can rewatch it again if you need to.
Okay.
This here is the inverse. That's what we have. We have the inverse. They want us to plug it into g at x and then isolate. So I'm going to go through this part a bit quicker.
Wait, isolate for what? Like x?
They want us to isolate for x. They've given us an
Oh,
answer.
that's
Instead of giving us an input, they've told us what the output is and they've told us what would the input need to
Wait.
be.
Where's that from?
That's from the question we pulled off of your page there.
Nuh-uh.
Hmm.
Wait. Wait, the 5?
Yeah, if you
For
flip
what?
over,
Oh,
that's what that
How did
question is
you, like,
asking you.
notice that. Oh,
Yeah.
I didn't even know about that.
Yeah, it's a trickier
that was
question.
that was like secret as being like Jacob.
So let's plug it in. I'm going to take it and plug their inverse function. That's going to be the input to the g at x function. So essentially, this is going to look like this. G of 3x over x minus 1.
Okay.
I know this is a lot. And then we're going to replace the x with what our input is, which is 3x over x minus 1. Now, luckily, there isn't much we have to do here. In fact, I don't really combine those. That is what it's going to be. So our g of the inverse, not yet, buddy, I'll talk to you after. Okay, is equal to 5, which means this is the new function. We've just found it. We have to set that equal to 5. So 3x over x minus 1 is equal to 5. We have two x's. This part's going to be tricky. So I'm going to move my 1 over, in which case I add 1 to each side. So on this side it cancels out, and when we add 1 here we get 6. Now I got to employ that trick I did again. I got to get rid of this denominator. So in order to move it over, because this is division, it needs to be multiplied when it comes over. Okay? When we do that, this will disappear and we'll be left with this side. So we'll have 3x is equal to 6 times x minus 1. I'm going to distribute. So we'll get 3x is equal to 6x minus 6. I need to get my x values by themselves, so I'm going to move this x over. This will become 3x minus 6x equals negative 6. We're going to collect our like terms. This will become negative 3x is equal to negative 6. I need to isolate for x, so negative 3 divided on both sides. And we get a value of x is equal to positive 2 in this case. So we got to take a look at what your answer was, because I'm pretty sure the answer they gave you was pretty different from that.